start the presentation. Good luck.
Okay, thank you. Well, hello everyone. I'm Matías Vara. I am here to talk about some of the work I did in the last couple of months regarding some work I did to improve the booting time of the Toro kernel, which is a kernel dedicated to run on virtual machines. Can you hear me well?
So in general, there are no speakers here.
Okay.
You need to speak a bit louder.
Okay.
The mic is only for the live streaming.
Okay, cool. So what is exactly Toro is application-oriented kernel, which is made of more or less 5 mainly units, which are process memories, file system, networking, and these units provide a simple API for the user application. For example, if you see the process unit, we'll see machine thread, tree thread, all the manipulation of the thread. If you see a file system unit, we'll see some API to manipulate files and so on. In the case of microservice, which is as you may know, it is a user application, we propose to compile the microservice together with the kernel, and this results in a single binary. The microservice can decide which are the components going to include in this binary. And that is done directly from the syntax of the microservice. So, for example, in this case, I say, okay, I will include memory, file system, I don't know, the extension driver and the Intel Gigabit driver. As the result of this, we generate a binary, which is an ELF. And from this binary, we have a set of tools in which we can first generate an image, and by relying on another tool called Cloudy, we can then launch a virtual machine, right? And to demonstrate that all this work, I will just show us a simple demonstration. Here, for example, we have Toro running in a simple microservice, which is serving index HTML. For example, here you see the results. So what you see here is more or less the initialization of all the drivers. Sorry, we crossed here. The initialization of all the drivers and the networking and so on. And then from here you see the user application start to execute. If we come back to the slide. So actually, we spent some time to first compile the kernel and the user and the microservice, and this takes more or less 1 second because it's only compilation and then generate the image. And we take another 1.5 seconds more or less to boot the virtual machine. And here I'm taking into account the time the door is open. And here, this time is just that the kernel starts to execute, but not after that. It's just until the kernel mine starts to execute, for example. The image in the current state is around 4 megabytes. And so what we figure out, but I figure out it as this time limits a lot if we wanted to use kernel for example, continuous deployment of microservice, or if we wanted to instantiation on demand of microservice because we need a fast instantiation. So if we see more in detail how is the booting process of Toro, you see first the virtual machine monitoring initialization, which includes, for example, initialization of the device model, BIOS, and other stuff. I'm not pretty sure about this. Then you have the bootloader that is already part of the kernel, which is initialization most of the hardware, the processor, SHA-2 log mode, enable paging, read the kernel from the disk and then put it on memory. So this talk, I'm only going to talk about the work that I did, which was focuses on these two first steps. In the next slide, I'm going to talk about how we try to improve this time. So yes, I will start talking about how I improve the bootloader. Then the virtual machine, the initialization of the virtual machine monitor. I will present some tests that I did, and then I will conclude. Well, the problem that I had at the beginning was that, as you can see, the generated image that include the user application and the kernel was very big. And this was like this because in order to make the bootloader simpler, what we say is the image will be the copy of the kernel in the memory. So the whole, an image of the kernel in memory. And we did it like this because make simpler the bootloader because you just need to read the image, put it in memory. You don't need any data compression or something like this. But the main problem of this is first, you end up with an image that is huge, as you can see, was 4 megabytes. The bootloader is still complex because you still need to initialize some hardware, any paging, and so on. So the proposal, what I'm working on, was to use the -kernel option which is proposed in Kivu KamiM to load the kernel. And I will explain a bit what is exactly this. Actually, what you can tell Kimu is you can pass the binary, which must be a multi-boot kernel. And what is exactly going to do? Kimu is, well, this is not exactly like how the binary is, but I'm using this picture just to illustrate a bit. So actually in the binary, which must be a ELF32, you have for sure all the section, and you need some sort of a special header that Kimu is going to read. From this header, it's going to read all the section of the binary and then put it on memory. This is the memory of the virtual machine on the guest. When Kimu start to execute the multi-boot mine, which is a point in the xtext section, the processor is already in protect mode. So most of the hardware is already initialized. So all that feature that you need to implement in the bootloader to initialize hardware, you don't need it anymore because you already have there. And then at some point you will start to execute the kernel, right? So the benefits of using this option that have Kimu were many. For example, I could reduce the size of the mesh from 4 megabytes to 130 kilobytes because only include the binary, right? That reduces a lot of the complexity of the bootloader because you don't need to jump to protect mode and some stuff. So because Kimu is already doing this for you, and also since you don't have to read the whole image from this and put it on memory because Kimu is doing this, you reduce a lot the booting time. I started with 1.5 and I end up with half second to boot the image, the kernel. The main drawback of this is that, well, not all virtual machine monitors support the use of this feature. So at the end you're porting your kernel to that virtual machine monitor. Second, Kimu only support ELF32, so you need some sort of magic to put ELF64 inside ELF32, which is extra work that you have to do. Still, when the kernel starts to execute, it still is in protect mode. If you want to use 64-bit, you have to go to log mode, and you still have to do such initialization in the bootloader. So it is not that you can just start to execute the kernel. Some people were working on this more precisely in a project called Kimu Lite. We try to add these features to Kimu, so you don't need to enable log mode because when you jump to the kernel, it's already log mode. So reduce a lot of also the complexity of the bootloader. But they stopped to work on this I think 1 year ago. If you see the port that I did for Toro, you can find it in that issue in GitHub. I stopped that 1 year ago, I think. So the next topic I want to talk is how I work around the virtual machine monitor to try to improve the initialization. So actually what I did was I studied three approaches to try to improve the virtual machine monitor. These approaches are based on KVM, Kimu, and these are Keyboot, Nimu, and Firecracker. Maybe you know already then. The big picture of these approaches is that they try to improve some aspect of the virtual machine monitor. For example, simplify the loading of the kernel, or some reduce the device model. So I think they tackle different aspects of the whole virtual machine monitor. And to talk about these approaches, I wanted to first introduce some concepts here. When you have the kernel, the Linux kernel, the KVM driver, which provide all all the virtualization features. Then you have the virtual machine monitor, which provides, for example, device simulation BIOS to the guest, and then you have, for sure, the guest in guest mode. So the first approach I want to talk is KeyBoot, which is also based on QEMU. And the idea is that propose a firmware which is much more optimized. The only drawback that they present, I mean, there are not a lot of information about how it's exactly is the optimization, but one of the drawbacks that they present is, for example, they limit the size of the kernel that you can load. It is 8 megabytes, and you can find more information there. Which is cool with this is that you can just boot it. I mean, you can just compile it and then use it by passing the minus BIOS with the firmware. The next approach that I tried was NEMU, which is based on QEMU, but they only focus in 2 platforms. And the idea of this project, at least idea that they gave me, was that they tried to reduce all the device model in order to reduce the attack surface, and also for example, the memory footprint of the virtual machine monitor. Also, they propose a new virtual machine, a new type of machine, which is named BIRD. And to use this virtual machine, you can only boot from USB. I didn't not work too much on this, but you can find more there. That link I use it. And the last approach that I tried was Firecracker, which is, I think they started to be public on December, I think. The nice thing here is that they don't have any device simulation. All the hardware is based on Virt.io. What is also nice is that you don't have this multi-boot feature that has in QEMU, but you can, for example, give Firecracker an ELF64 binary, and it's going just to start the kernel, and the processor is already with patient enabled and 64 long model, which is quite nice. So that reduces a lot of the hardware initialization I had to do before I execute the kernel. So how I compare these approaches? Well, the test was quite simple. What I measured was the time from I launched the VM until the VM is shut down. And to shut down the VM, I just added some code in the kernel main. And then I did this for the 3 approaches, and then compare the time. If you want to see more about the script that I use, you can see here. For sure, you can give me some comment about the script, because it's just, yeah, it's sort of a sketch. So that is the test, the result that I have. This is the hardware that I use it. And the one interesting thing, but there are many interesting things that you can see here. For example, here you have QEMU, where I use the 4 megabyte image, and then you can see the difference when you start to just use the binary. I mean, that is reasonable because you're reducing a lot the binary I had to load on memory. And then you can see that you have a 300 millisecond that you get if you use KeyBoot. Then you have NEMU, where you see a difference of 152 milliseconds for QEMU. I don't know why, and then you have a lot of difference when you use QEMU. And this is really interesting what you get by using Firecracker, because it's only take 27 milliseconds to start to execute the kernel mine. And it's just I noted that I leave here just to compare, as have in mind the times. For example, if you follow this blog and you check how much time is spent in an echo, it's more or less 2.5 milliseconds. So, and here you have a whole virtual machine, sort of micro virtual machine, how they call it. So yeah, I'm going to conclude. So what I get is, when we use a solution that is a combination between a multi-boot kernel and KeyBoot, which is a firmware which is optimized, you see an improvement of my current bootloader of 11, yeah, a factor of 11. I agree that my old bootloader was a bit crap, but still. Then we have a factor of 85%, 85 when we try with Firecracker. And my impression is that the choice of one solution over another is just a trade-off between the need that we have to do to adapt the kernel to that solution and the resulting booting time that we want to expect. So yeah, that's me. I don't know if someone have any questions. Maybe it was too fast. Yeah.
That's what you fast kernel, faster presentation.
That's it. Yeah.
Have you ever tried KVM tool?
Sorry?
KVM tool?
No.
Never
I
tried?
didn't try it. Sorry. If I had tried KVM tool. No, I haven't. They told me to do it a couple of days ago, but I had no time. But I will do it next time.
Good question. Implementation is in assembler and Pascal.
Implementation of what? Sorry.
Toro.
Sorry. Yeah. The question was if the implementation was in assembler and Pascal.
Yeah.
The implementation of what?
Toro kernel.
Well, they have, a part of assembler, a part of Pascal. Yeah. I mean, all the work that I present here is most on the bootloader, so it's most assembler. So. So, if you have no questions, that's all.
You
Okay.
can mute the mic.